So this is our LTI system, and I'll write bracket h of n inside it, and this h of n is the discrete time impulse response. This is what we get when we transmit an impulse in the input, and output comes h of n. So this is the analogous to the continuous time. In this discrete time case, the input is simply the discrete time impulse, that's all. And the output is only discrete time. This is still called the impulse response. We then perform discrete time Fourier transform, and the word discrete time Fourier transform is a general term. Fourier transform encompasses Fourier series as well. So we say discrete time Fourier transform of h of n, and we'll get h of e j small omega. Now, notice the notation has changed. This is h of n, this is small omega. In the continuous time case, I'll draw for you again. This is h of t. This is continuous time LTI. And when we want to perform continuous time Fourier transform, we get h of j big omega. So please observe the notation change. When we are playing with continuous time, the omega is in capital, and here we implicitly understand it as 2 pi big F radian per second. Here, the small omega is small w, and the unit is radian per sample. By comparing these two, we are not confused whether we are in discrete time or continuous time. Now, he has a name, and his name is the frequency response. Okay? And one more. If we perform the Z transform of h of n, we get h of z, and this guy is called the transfer function. What does the frequency response means? It means it will tell me how this system LTI behave along different frequency. Here is frequency. It will tell me the gain that will, for example, if I send a signal e j omega 1 n, this is a signal at frequency omega 1. I will look at omega 1 along here, and I will read off this, for example, A, and I know that if signal 1 e j omega 1 n is passed through this system, out comes A e j 1 omega n by reading this frequency response. So the word frequency response means exactly what he says he is. He will tell you how the frequency will behave when it passes through the system. Not only are we interested in amplitude, we're also interested in the phase, the angle at h e j omega. And we can read off at w1 again, and maybe here is minus pi over 3. So for this signal, 1 e j omega 1, he will come out A because of this, but he will also come out with e j minus pi over 3. A phase shift of minus pi over 3 is introduced in this phase diagram.